In this concept, we're going to talk about similarity in right triangles. So if we have a right triangle and we draw an altitude from the right angle to the hypotenuse, right? So we have right triangle ABC, and we draw the altitude AD, then we get three similar triangles. Okay, they're similar in that the ratios of the sides are similar. So in the figure above, triangles ABC, ADC, and ADB are all similar to each other. Let's learn about the concept of the geometric mean. And this is important because it will be an important tool, again, in doing calculations having to do with triangles. Okay, so the geometric mean of any two numbers, A and B. So, for example, these numbers could be, the lengths of the segments of a triangle. But in general, the geometric mean of any two numbers can be found using the following proportion. So, if you have numbers A and B, you set it up like that, right? So A over X, with X being the geometric mean, is equal to X over B. Another very easy way to remember what geometric mean is of two numbers is it's essentially the square root of the product of the two numbers, right? So the geometric mean, in this case X, is the square root of the product. So write the product, take the square root of it, that is the geometric mean of any two numbers. Let's look at some examples. Find the geometric mean of 12 and 3. So again, you can set up the proportion as a fraction, or you could just say it is the square root of the product of 12 and 3, which is 36. So what is the square root of 36? So it's 6. So the geometric mean is 6. 9 and 6, right? Same thing. You can set up the proportion as two fractions like this, or you can say it's the square root of 9 times 6, which is the square root of 54, which is approximately 7.3. And the geometric mean is always positive. Okay, that's something to keep in mind. Now let's see how this can be applied to right triangles. There are two important relationships of the geometric mean in a right triangle. So the first relationship is that the length of the altitude of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Right? So the altitude in this case is AD. So AD is the geometric mean of the lengths of the segments of the hypotenuse. So the hypotenuse here is BC. It is made of segment BD and segment CD, right? So if we multiply these, if we take the geometric mean of these two segments, of the lengths of these two segments, right? If we take that geometric mean, we get the length of AD, the altitude. So, again, using our simple method of writing geometric mean, we can write this as AD equal. So again, you can set it up as the proportion, or you can say, again, AD is the square root of the product of CD and BD. Okay? Both ways are correct. So you can see this is a very powerful tool for finding sides, lengths of segments and lengths of sides in a right triangle. Let's look at this example. Find the length of AD, which is the altitude. So we're given the hypotenuse. The segments of the hypotenuse are 4 and 9, BD and CD, and we need to find AD. So again, we can just say AD is equal to the square root of the product of the segments. So 9 and 4 gives us 36. Square root of 36 is 6, right? So AD is equal to 6. The second property of geometric means as they apply to triangles is that the measure of the leg of a right triangle So let's say something like AC, right? Let's say this leg is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse adjacent to the leg, right? So AC is the geometric mean of the length of the hypotenuse, which is BC, times the segment of the hypotenuse adjacent to the leg. So we have AC, the segment of the hypotenuse, so the hypotenuse has two segments, CD and BD. The segment that's adjacent to the leg of interest, AC, is CD, right? So we want this leg. They're not equal, by the way, I'm just marking it. So BC times CD, right? Square root of BC times CD is equal to side AC. Okay? Or again, we could have set it up as the proportion, right? So BC over AC is equal to AC over CD. Okay? Let's look at this example. Find the measure of side AC. So again, we have the hypotenuse, BC. So the full hypotenuse is 11 units. The side, or the portion of the hypotenuse, or the segment of the hypotenuse adjacent to our side of interest is segment CD, which is 7 units. So CD is 7 units. So AC is equal to the square root of the product. Again, 11 times 7. Square root of 77, which is approximately 8.8. Okay? And also, so we've done side AC, we could also do the other side, the other leg of the triangle, AB instead of AC, by taking the full hypotenuse and then the other segment of the hypotenuse now that's adjacent to the side of interest, right? So to get, let's visualize this a little more. So to find side AC, we took the full hypotenuse and the segment that's adjacent to side AC, right? And we took the geometric mean of both of those segments, right? This segment and the full hypotenuse. Now to find side AB, we take the full hypotenuse and the leg that's adjacent to side AB, right? You take the geometric mean of both of these two segments. Okay? Here's another example, finding the measure of AB. So the full hypotenuse here, BC, is 15. The segment that's adjacent to side AB is BD, which is 5. 15 and 5. So we basically need to find the geometric mean of 15 and 5, right? And that gives us side AB. And we need to find the measure of AB. So AB is the square root of the product. Again, 15 times 5, square root, which is the square root of 75, which is 8.7 units. Okay, so AB is 8.7 units. Okay, and here we have some exercises. Please pause the video, work on these, and come back for the solutions. Okay, find the geometric mean of the following numbers: 10 and 14. So again, remember, the easiest way to find the geometric mean is the square root of the product of both numbers. So the square root of 10 times 14 is the square root of 140, which is equal to about 11.8 approximately. 3 and 7. Again, the Geometric mean is the square root of 3 times 7, which is the square root of 21, which is 4.6. Okay. Next example, use the figure below to answer the questions below. So we have triangle ABC, and we have the hypotenuse BC, and we have the two segments of the hypotenuse, BD and CD, 5 and 10. Okay? Find the measure of AD. So we said that AD, being the altitude, is the geometric mean of the segments of the hypotenuse, which are 10 and 5. Right? So it's just the square root of the product. So the square root of 50, which is about 7.1. Find the measure of AC. So again, AC is the geometric mean of the full hypotenuse, which in this case has a length of 15, BC, 15, and the segment closest to the side of interest, AC, which happens to be CD with a length of 10. So AC is equal to the square root of the product of the full hypotenuse, which is 15, and the segment closest to the segment to the side in question, which is CD, 15 times 10, a square root of 150, which is 12.2 units. Okay, and this is it for this concept. See you in the next video.